Before we start with the presentation, let me briefly introduce the experience sharing focus groups of ENOS. As you are most probably well aware of, is that this activity is part of the ENOS project. I'm almost sure that most of you are aware of what ENOS is, but if this is not the case, just please go and visit our website at enosproject.eu when you can learn more about our project. Experience sharing focus groups is an activity that is related to the ENOS objective: establish partnerships and share experience and knowledge with groups and entities executing onshore CO2 storage pilots, demonstrations and leakage simulation tests in Europe and worldwide. And the purpose of the groups is to share experience and recommendations around various specific topics. Our groups are open to all researchers and all pilot sites, and these topics of these focus groups are in fact not the same as research priorities, as we can also include practical issues, and the goal is to remove hurdles to running a successful pilot site. We have planned at least 7 webinars, and this is the second one of them, and 3 workshops for this activity. On the ENOS website, we have a dedicated web page on this experience sharing focus group. That you can see the address, which is a bit complicated. But when you arrive at the ENOS website, which I now am going to show you briefly, you can find it in the activities part of the website. And if I'm successful, you will now see the web page that is dedicated to the experience sharing focus groups. And now something went wrong, and you can find here some brief description of the activity. You have find here a tentative time schedule, and you have here information about the activities that have been carried out already. So you can see some information about the first workshop we have had in Venice in May last year, with some minutes presentations and photo gallery. And you have also a link to information about the first webinar that was held in December 2017, and the focus of which was data archiving and management. And if you click on the link, you can see this detailed information. And what is the most interesting here is that you have access here to the recording of the first webinar. And we are going to arrange today's webinar in the same way. That means if you are interested, or some of your colleagues want to look at that, or for those who were unable to attend, you can see the video recording here on this web page. Here you can see the plan and tentative time schedule of our experience sharing focus group activities. So you can see that we are here, marked by the arrow. So we have had the first workshop and webinar, and we are now about to start the second webinar. And you can also see the plan with the next ones and the next workshops. I will not read it. You can find it on our website. But you can also see that we have already predefined the topics of the upcoming webinars and workshops, but there is still one topic missing. So feel free to suggest a suitable topic for experience sharing and discussions for November 2019. We are open to your suggestions. Now I would like to take the opportunity to invite you to the second workshop of experience sharing focus groups. This workshop will be again attached to the CO2 GeoNet Open Forum and will be held on the 23rd of April in the afternoon. This is Monday, and the topic will be advanced techniques for site characterization. The program of the workshop is not yet complete, unfortunately, but we have already a few topics and speakers confirmed. So, as you can see, you can meet there representatives of Silixa, who will be presenting VSP using fiber optic acoustic sensors at the Australian Otway site. We will have Anton Šipanov of IRIS Norway, who will present on well testing and pressure monitoring, and we will have Carlos de Dios from Sweden, who will share his experience from light drilling applied to Ontomine. And what is especially interesting, he will talk about technological gaps detected. And there will be 2 or 3 more presentations in the workshop, including one on the latest results from the site characterization at the Sulcis site on Sardinia. As I mentioned, this second workshop will be part of the CO2 GeoNet Open Forum, and to register you have to go to the Open Forum registration website. The link is here. And here you can register not only for the conference, but also for the workshop that will be held, as I said, on Monday. It will be just one day before the main Open Forum conference start. And we will end with the workshop just in time for you to be able to participate in the Open Forum icebreaker reception on Monday evening. So let us come back to the webinar of today. As announced, the topic is smart drilling for CO2 storage sites, reduction of costs. Maybe before we look at the speakers, let me spend a few words on explanation of the term smart drilling. So for the purpose of this webinar, I think we should take it quite broadly, including any technologies, measures or approaches that are leading to increase of effectiveness, improved performance and reduction of costs related to drilling and other field activities related to wells. So as you can see, this is a quite broad definition, and I strongly hope that you will get a lot of interesting information from our speakers that will be presenting today. We will have 2 presentations where our speakers will share their experience with drilling of wells at CO2 storage sites, and our speakers will be Kim Senger from the University Center in Svalbard, Eugene Holubniak from Kansas Geological Survey, and Carlos de Dios from Sweden on the Ontomine pilot CO2 storage site. So this was a brief introduction to our webinar of today. So now I would I would like to ask you if anybody has a question. So you can, as I said, you can either raise hand using the button, or you can put it in writing in the questions box. So at the moment, I do not see any questions. I hope I have checked thoroughly. So I think we can move now to the first presentation. And due to the fact that we have some connection issues with Kim Senger, I will now give the floor first to Eugene Holubniak of Kansas Geological Survey, who will share with you experience from Kansas regarding their drilling activities. So I have now to push the right buttons to change the presenter's role. Hopefully I will do it the right way. Yes. So now also your microphone should be on, Eugene, and the floor is yours.
Thank you, Vlad. My presentation will be pretty short today, and I would prefer questions after the presentation, because we've done at Kansas Geological Survey, and I'm Eugene Holubniak. I represent Kansas Geological Survey, and the Kansas Geological Survey has done quite a bit of work in realm of both CO2 sequestration and CO2 EOR. And though those two activities are very related, despite what people might think, they are very much connected, and drilling for EOR is not very much different from drilling for the CO2 storage. And especially if you're considering monitoring and other things. And Kansas Geological Survey has performed quite a few projects related to drilling and characterizing sites for CO2 storage and EOR. So I'll start. Basically, this is a summary of 3 different projects, but we had Kansas Geological Survey had quite a few other projects with the Department of Energy and other entities related to CO2 storage and EOR activities. And on this slide, you can see the amount of people who were involved in these projects over the course of many years. So, in summary, I have a few things to say about our Bemis Schatz projects, where we were trying to land the horizontal well in a carbonate reservoir. And this horizontal well, the purpose for drilling this horizontal well was to understand the paleokarst and to verify the volumetric curvature tool processing, seismic processing in a carbonate setting, to test if we could see the structural features for this carbonates, and see if we can actually computate the amount of fractures and align those fractures with the things we see on seismic. And as well, we did an extensive logging program for that well. Also, we drilled one well related to the Wellington, actually 2 wells related to a Wellington study. One for the storage project that actually never came to fruition because of our problems with the permitting. As you may know, it is difficult to permit the Class 6 permit for CO2 storage in the United States, especially for research projects. And so we went through all the series of regulatory meetings with the EPA, and we pretty much came to a conclusion, but where we stumbled, was the financial responsibility. But so the well and the site characterization was fine, just a money issue. But nevertheless, we drilled that well 128 for the storage, and we did quite extensive well testing and logging and correlating logs of seismic and so on and so forth. And also related to that site, we did the regional study looking at the large-scale aquifer to test and see if, because there is not much information in terms of well control or any log data or core, it was not existent. So we did the 2 wells, 132 and Qatar wells, which are about 250, maybe 300 miles apart, to characterize this Arbuckle aquifer in Kansas. And also because we are involved in constantly trying to apply for more funding in order to do more studies in our area related to CO2 storage, we stumbled upon a few other new methods of drilling that you might consider. One of them is slim holing, especially if you're drilling and you need to recover core and or to establish monitoring wells. A lot of times it might be worthwhile looking into those relatively new technology. Well, slim hole was used for quite some time, but in recent years, the price for the slim hole in both coring and drilling came down quite a bit. And so if you consider comparing prices for the regular size and the regular drilling techniques and slim hole, the price point could be attractive in terms of the going for the slim hole. And recently there's this is more recent development, radial jet drilling. You might, if you want to increase your if you would like to increase your injectivity index in your wells and or want to drill extensive horizontal with stimulated horizontal wells, the radial jet drilling might give you an advantage in this case. And we did spec a few wells with both the slim hole technology and radial jet drilling technologies, and in recent years both prices kind of collapsed quite a bit. So now in a little bit more details, I'll show you where we actually drilled and what kind of sites you might find on our website. And basically, I cannot put all this experience and I cannot share with you over the course of 15 minutes everything we did. So I encourage you to visit our website, which will be provided at the end of this presentation. But here I'll give you just a brief overview of what happened and what kind of projects we were related to or we performed on our own. And the first one, the Bema shots, is, yeah, I hope you can see my my mouse here, but this is in the central Kansas uplift region. All right. So in this central Kansas uplift region, you can see the Bema shots field, which is outlined in blue. And in this field, this is a very interesting Arbuckle carbonate. We drilled this horizontal paleokarst well for reservoir characterization. And another reservoir characterization well was drilled in Qatar field in the western part of the state, and so it's on your left side of the map in Hugoton field area, in the area of Pleasant Prairie, Eubank, and Shock fields. And the Wellington site is located in pretty much south central Kansas. And in this area, we had 2 more wells that were drilled on site, and for the storage projects, and 1 more well that was drilled for the EOR activities. So here's an example of the well, that horizontal well, and why we drilled it. As you can see, we tested the paleokarst, and the main reason was to see if we could both outline the isopac and the seismic together to make sure that we see some of the paleokarst features. And we could recognize those features, and then after that we decided to drill the well to perform even better characterization. So for that purpose, we drilled through one of those features that you can see on this isopac and on the seismic on your right. And that was a very successful project, because after that we could really outline the karst features and quantify the amount of fractures that are related to this paleo cavern. And then we sort of upscaled this analysis for the entire field and came up with a map of fractures and faults in the field. And this is in a little bit more detail what resulted in this configuration. And here is the resulting map of faults and features that we were able to produce based on this characterization well that we drilled. Here's another example of why we drill wells. And again, this is we're drilling in carbonates, and so in carbonates, all the program that you're developing for drilling will be maybe a little bit, not maybe, but I would say strongly that it's going to be very different from the clastic setting. So in the clastic setting, you might choose one set of tools. In the carbonate setting, you will definitely need to choose another set of tools that you decide to run through your well. So it's everything related to the well drilling. You will also need to consider the cost for the well logging, at least, and or well testing. And in carbonate setting, well testing is strongly encouraged and recommended. But in our case, we could say that in terms of logging, the nuclear magnetic resonance was very helpful, because we could understand the pore sizes better, and the imaging logs were also essential in this program, because we could do not only stress analysis based on induced fractures, but we also could see the fracture distribution. And because we had a luxury of core, we could quantify core, but we could correlate it with what we see through the image log as well. And so on your right of this, for the slide, you can see all the key well logs that we would recommend in the carbonate setting to characterize carbonates better with well logs. Here's you can see the core, and because we are very we're relatively shallow. We're only about 5,000 feet in this case, and 7,000 feet in case of Qatar. We were able to core extensively, and so we took about maybe 1,000, maybe a little bit more feet of core. So it's more than 300 meters of core in this case. And again, because the prices for coring came down in recent several years, came down quite a bit. But I'm not sure if it's going to be the pricing for the coring operations and drilling operations could be different in Europe. But in our case, because of its shallow and because it's a mid-continent, in order to drill a well, I will name you the approximate number. In order to drill a well, core it, and log it, the entire suit, we paid on the order of $1.1 to $1.2 million to the depth of about 5,300 feet, and a similar price, maybe a little bit more expensive in terms of cutter well, where we drilled to a depth of about 7,000 feet, and we took a little bit more core, so we paid about maybe 2 million in total. And we also drilled for the CO2 EOR well, and that well was a little bit less expensive because it was, again, project specific. We took only about 90 feet of core, and we logged it only specifically for the EOR project. And this is how it might be different in terms of the price point for you is if you optimize it for the EOR, you probably could do a little bit cheaper than you go at the full scale scientific well, and that's understood. So here is the scatter well and a few examples of the core laid out, and basically any company that you use, it's either Halliburton or Baker & Hughes, or will have different, a little bit different setup and shop for the core handling and for the drilling, but the price points at this point are pretty similar. So I encourage you to visit our website, and if you have specific questions about aspects of drilling, please don't hesitate and ask me. I will try to accommodate you.
Thank you very much, Eugene. I think this was quite a presentation of practical experience, which is of course appreciated. So now we have time for questions or comments. So I cannot see any questions typed in the questions, but you can still raise hand if you have a question, and I can unmute your microphone. Or if you are a panelist or presenter, you can just turn on your microphone and ask directly, because you have better rights than the usual attendees. So please, are there questions on Eugene? I cannot see any, unfortunately, which is disappointing, I must say. Yes, I can see some questions. The first one is by Yann Le Gallon. The question, I'm not sure if I can interpret it well, but maybe I can try, and if not, I can unmute Jan's microphone. So the question is, what type of logging do you recommend for carbonate? Was it okay?
Sure. So if you go to the slide, this one, I hope you can see the same. You can see the same slide as I am. On the right side, there's a list of logs that we would definitely recommend. And in our experience, the nuclear magnetic resonance was one of the. You need to do it carefully, because you need to pull the tool through the strata a lot slower than most companies are usually are doing, because in order for nuclear magnetic resonance to work properly, you need to identify your time the tool spends in a column. Otherwise, you might get data that is not very much useful. So you need to be careful on how you set up your nuclear magnetic resonance logging survey. So it might cost you a little bit more, but especially if you're doing, if you're in an area where there's not a lot of activity in terms of, oil wells and are not drilled, and you don't understand porosity or permeability very well, like in our case in Arbuckle, there's not much activity, or people are drilling but they're not sharing logs. So you need to be very careful on how you have only a few shots, you have 1 or 2 wells that you could drill, so you need to be very careful on how you characterize each and every well log, and that's why the planning for the well logging is very important. So you go into when you go into nuclear magnetic resonance, you need to model your strata first. So you need to sort of understand what kind of response you will get from your carbonate, and then after that, say, please pull it with the I don't know, 15 seconds per certain amount of the interval in the well, and they will be very grumpy because they usually don't do that, but they'll do it if you ask them, because you pay money, and that's what they care about. And so, and then the whole suite of logs it could be pretty usual. Pretty usual. You could add those more sort of scientific, or how to say, not your usual type of triple combo type of logs, but you need to correlate all those exotic logs with the regular ones, and you need to design the survey again pretty carefully. So the NMR is very micro-resistivity. We use it quite extensively in all our cases. And the imaging logs are, again, very helpful, especially if you're doing mechanical analysis or don't have core. And even if you do have core, you still want your imaging logs to be run, especially in areas where you don't have much understanding of the strata.
Thank you, Eugene. I think this has been a quite exhaustive answer. I hope Jan is satisfied. And we have another question by Ton Wildenborg. How do the costs compare to drilling for oil and gas exploitation?
Well, again, it depends on it, and I could actually share numbers because we quoted wells quite extensively throughout those years, and I personally quoted quite a few wells. So first, the numbers. The 2 wells we drilled for the purpose of exploration. Costed, again, depending on your depth, but one well was about 7,500 feet, and another one was around 3,300 feet. Those 2 wells, you could safely say that we spent for both the logging, coring, and drilling. So the entire set program for drilling. In the first case, where the well was deeper, we spent about the bulk number from 1.2 to 1.35 million dollars for one well, and another one well costed us about 1 to 1.1 million. And that was at the time when the drilling was sort of picking up. And so it also depends on the time in the oil industry, at least in our case, in case of United States. It is very sensitive to the amount of drilling people usually do. So if they're very busy, your costs go up. If they're not very busy, your costs go down. And so for the well, which was drilled for the EOR, it was a lot shallower, or not a lot, but shallower. Let's say 1,000 foot shallower than the 3,300 feet well. So we drilled to a depth of 3,700, and we cored it only a little bit, and we took just and our logging was a little bit less extensive. So we were interested only in the reservoir portion of this well. For that well, we spent about less than 600,000, and we spec'd similar wells recently. And because of the cost of drilling came down in recent years quite a bit, and although activities are starting picking up in the United States, but they're not at the level of 2012, let's say, or 2013, 14. Similar well that was spec'd recently for us, the cost was about 600 before. Right now it's roughly 500,000. And on top of that, I could tell you the slim hole drilling, which could be used for monitoring and or coring. And if this basically this 6 to 500, 500 to 600 for oil and gas activities wells to the depth of about up to 4,000 feet would cost you in slim hole, depending on your diameter. It varies quite a bit, but the cost could be about 350 to a maximum of about 400,000 in our case.
Thank you for the answer, Eugene. And there is one more question by Kerry Vincent. I will try to read it correctly. Maybe I missed this, but did you show an example comparing logging open hole and through casing logging at your site? I'm interested to see the impact of casing on your logging results and to compare to results in classic reservoirs, since you said that the tool suite is different.
Right, that's for sure, but I will tell you this. Yes, the suit will be different, but and we did both the well, the open hole well, and the cased wells. We did log of both of those, and I'm not a petrophysicist myself. I do have a on-staff petrophysicist, and he would address your question a lot better than I can. But you could also take a look at our website that I shared in this presentation, and there are a number of examples, a number of wells that that were drilled, and you can see them in reports and see the suits of well logs that what we have chosen for both of those. But I will not speak for the petrophysicist here, and if you would like to, I'll set this question to John Dufton, who is our staff petrophysicist, and he can answer you in a better fashion than I can do.
Okay, thank you, Eugene. Of course, I would like to encourage both of you, I mean you and Kerry, to interact, especially taking into account that you at Kansas Geological Survey are one of our twinning partners in ENOS. So I would really like to encourage you to exchange more, starting with this topic. So this is now, but this is now up to both of you. So just go ahead. So as I can see, there are no more questions at the moment, and I cannot see any raised hands. Hope I didn't miss anybody. So thank you very much, Eugene, once again. And
thank you.
And we will now switch to the next presentation. We managed to connect our colleague from Svalbard, Kim Senger. He might appear under an alias because he was only able to join us under my personal credentials, so maybe you can see some misinterpreted subtitles like that myself is presenting, but this will be Kim Senger. I will now try to make him a presenter. So Kim, could you please confirm that you are online and that you are able to share the screen? Yeah, I will now unmute your microphone, so you should be online now.
Yeah, do we have takeoff?
Yes, please, the floor is yours.
Wonderful. Thank you, Vít. Thank you to the listeners. So I haven't been eaten by polar bear, just haven't had the link. And I'm gonna try to give you a little overview of CO2 storage project here at Svalbard, which has been running since about 10 years, started in 2007. At that time, my good colleague Alvar Bråten, he set this one up. He is now in Oslo, and together with also another petroleum geologist called Snorre Olausen, we've been working on this a little bit. And this project has at the highest activity involved most of the research institutes in Norway and away. And to put it a little bit in perspective, we have spent about 10 years, roughly 10 million euro, and half of this money has come from private kind of fundings, which was involving oil companies like Statoil and Lundin, service companies like Baker Hughes, who stood for the testing, and also some of the local companies like LNS and Stora Norske. So let me just get on with the conclusions, just in case somebody drops out during, so you know what we have found. We have found both a siliciclastic or sandstone dominated reservoir at relatively shallow depth of about 670 to 970 meters depth. We have also found a cap rock above it, which we have tested to be sealing, a robust top seal on that. We have injected fluids, unfortunately no CO2 yet. I'll come back to the reasons for that, but we have injected water. It's on this image here, you see one of the water trucks which we used in this injection test, and we have confirmed fluid injectivity. And we have also calculated storage capacity. Our reservoir, even though it's quite shallow, it's been buried much deeper in the past, and it's relatively low matrix porosity and permeability. So we rely on natural fractures to give us enhanced connectivity in the system. And in addition, what's been a little bit of a complicating factor was that during this drilling we encountered natural gas, which I'll come back to. So just for those who are not aware, where is Svalbard? Svalbard is a Norwegian governed archipelago at about 78 degrees north, here in the red star on the bottom right, and say we are within walking distance of the North Pole. It's governed by Norway, but actually all the countries who have signed the Svalbard Treaty have equal access to both resources and actually operating on Svalbard as long as they follow the regulations. We are roughly 2,700 people. Most live in two main settlements. One is where I'm sitting now, it's Longyearbyen, which is a Norwegian settlement, and you have Barentsburg, which is the Russian settlement. All infrastructure up here is here because of coal mining and geology. And even though we are so far north, we are actually relatively accessible. We have direct flights more or less every day. From down Oslo, it takes 3 hours to fly up here. And if you are lucky, you get a one-way ticket for less than 100 euro, actually. Well, if you're a geologist, which is what I am, you always love Svalbard. It's a paradise. It has more or less geological history, easily accessible, quite easily accessible also from Longyearbyen. And it's more or less what we say a window to the Barents Shelf. So we have a lot of sedimentary units from the Caledonian orogeny here in Devonian and up to more or less tertiary units. And there's different source rocks, different reservoir rocks, and Svalbard is a nice analog to the petroleum exploration further south. And as I said before, here this yellow part, both on the map and on the cross section, is the Central Tertiary Basin, which is the coal-bearing units. And all the settlements like Barentsburg here and Longyearbyen here are just located where they are because that's where the coal is. This DH4, that's the unit we have been, or that's the unit we have been testing for the CO2 storage, and the target here is this pinkish stuff. I'll come back to this. Essentially, yeah, we'll come back to these units. But when I talk about CO2 storage on Svalbard, of course, we are so far away, end of the world. It's always wise to think a little bit about putting things in perspective. And you know, many of you know that Norway is at the forefront of CO2 storage, but all of this is done offshore in the Barents Sea at Snøhvit, and also in the northern North Sea at Sleipner. And to put things into perspective, what we are trying to achieve here, this is the annual emissions of Svalbard. So you can see it. It's roughly 64,000 tons of CO2, which is emitted from the local coal-fueled power plant. So this is the only coal-fueled power plant in Norway. And anybody following Norwegian politics will also understand it's not a nice thing to be in a position for Norwegian government to rely on coal when they are also pulling all investment out of coal exploration worldwide. I also say, just to put it in perspective, this value here in Longyearbyen, which is emitted, is about 20 times less than what the Statoil and partners are injecting per year in the Sleipner. So this is the image of the power plant here. This is also the power plant, coal-fueled power plant in Barentsburg, which is another point source. And this is a kind of figure which I try to illustrate that Svalbard is the best at one thing, and that's actually per capita CO2 emissions. It's we emit more than 10 times more per person than mainland Norway. Of course, in absolute numbers, this is not so significant. It's a fraction of the Norwegian emissions. But what's important is that a lot of these emissions here on Svalbard are from these point sources. And of course, these point sources represent an opportunity. And this opportunity is what the project was built up on. That you have the coal mine here up in the valley, it's roughly 7 kilometers from the town here, where coal is mined. We mine about 25,000 tons of coal are mined there and burned in the power plant, which emits roughly 60 to 80,000 tons of CO2. And the idea was then to actually inject CO2 in the subsurface here. And all of these three kind of, not just the point source for the CO2, but also the coal which is used in the power plant are within a radius of about 7 kilometers. It's also important, there's no real land use conflict here. Groundwater, drinking water, there's no use of groundwater. Drinking water is from this lake here, glacier-derived lake to Longyearbyen, and we have support from the local politicians for this. So why do we decide where to drill? There was some seismic data, both industry and academic, mostly in the fjords, so marine seismic, but there has been some seismic acquired in the 1980s when there was oil and gas exploration onshore Svalbard. We have also acquired some of our own seismic. This is what it looks like when we go out and shoot seismic onshore. We have a belt wagon, and we have this 1.5 kilometer long snow streamer. And we use dynamite as explosives, which usually we have on the back of snowmobiles. And the challenge is, of course, you see from this map, this is the topography. So we can more or less just look at the main valleys, and also the very high velocity sediments. So these have been, even though they're quite shallow now, they've been buried to maybe 4 kilometers in the past. So very, very high velocities. And this reduces, of course, the seismic resolution considerably. So we can maybe map out the top of the reservoir, maybe the some of the regional reflectors, but we cannot go much detail. So when we decided to drill, the first drilling was done 2008, 2009. It was here where it says DH2. This is, by the way, the airport if you ever visit us. And the reason to put it there between the shoreline and a quite steep mountain was actually because that's the site of the town where the power plant is. So the idea was that if we have a reservoir, which we find characterized reservoir there, we can more or less just build a short pipeline here rather than having to pull the pipeline up there. We had some issues, come back to these issues, but we had some issues with these drillings. So in the end, we needed a bit more heavier equipment. We needed a bit more space. So we actually put our storage site into what we call the CO2 lab well park in the middle of the valley here. And here is the stratigraphy which we penetrate. So we begin in the lower Cretaceous, which is these green units here on the map. And we go down to these conglomerate sandstones, which would be the dark blue to pinkish units. The nice thing is, you can see from this terrain model with geological map on top, that we can actually look at these units also in the field. One of the big surprises we found that even though we expect things to be in communication, they are actually heavily under pressure. So there are some barriers in between. This is what the CO2 lab well park looks like. Here in the foreground is the lake we use for drinking water. Here are 6 of the 8 wells are within this relatively short, maybe 100-meter radius. This is a little bit the overview of how we drilled it. So this is done slim hole drilling. It's done with an exploration rig, which was used by the local coal mining company when they were doing exploring. So you essentially do this telescope approach, and you're getting at the same time as you're drilling, you're also getting your core material. So this is invaluable. Here's discussed previous speaker, something about costs. Here we are perhaps not so affected by, there's also a big onshore drilling market in Norway as in the US. And I think a cost of about $500,000 for a 1 kilometer fully cored borehole is very cheap when I compare to my experience from working in offshore oil and gas. We have also done these water injection tests, a couple of them including 2 wells. We looked at leak-off tests in the overburden to look at fracture pressure. We measured, we collected new 2D seismic. We also had some microseismic acquisition during the injection test. They haven't really resulted in any earthquakes, perhaps because there's some aseismic movement. And we also do a lot of detailed work on the core material, linking also the outcrop with the subsurface, trying to do reservoir modeling. And it's a lot of actually papers published, theses, master, PhD. We're running a course also on this. One thing I'd like to also mention, at last few years, the focus has been, unfortunately, not on CO2 storage as such, but because of this discovering natural gas, we had to focus a lot of resources and time on actually plugging and abandoning some of the wells drilled, here highlighted in red, to make sure that this gas doesn't escape to the atmosphere. So when we look at the drill course, stratigraphy, we penetrate. So these are the 2 sites. This is the one close to the airport. This is the one in the valley. This is our deepest well, the DH4. These are the units we have done the injection tests on, leak-off tests, and the reservoir is about 300 meters thick. It's Triassic to Jurassic age. It's a sandstone, net to gross of about 30%. There are some conglomerates in the system, some shales, which form as intra-formational boundaries, and there's some siltstones. The cap rock, roughly 400 meters thick, and what's the main seal is actually this unit here, which is between 2 formations. It's a major thrust fault, which is of Paleogene age, and that's the one which is holding the pressure difference from the upper part to here. Also note that we have a permafrost layer on top, and below the permafrost is also a small gas accumulation. The under pressure I mentioned before, severe under pressure at reservoir interval, slight overpressure above. Again, from a CO2 storage point of view, of course, this causes some complication in terms of what sort of phase you would be expecting, but it also implies that the top seal is quite good in that it holds this pressure difference. With respect to the logging was done in a relatively simple way. It was actually done by the Geological Survey of Norway. Of course, there are some issues with respect to the diameter you can get and whether you can actually fit your tools. So some of the deeper parts of the borehole are not logged properly. But we essentially have gamma, we have sonic, both P and S in some wells, and we have deep resistivity, temperature, and then from the cores we can derive porosity, DOC, and so on, so forth. We also unfortunately haven't logged through this lower part of this locality because of this decolomon zone, which caused us to lose some wells. When we go out into the field, this is what we see. Not this time of year, but in the 2 months of the summer when it's no snow on the ground, we see very nicely exposed. Longyearbyen is just behind the mountains here, and we see the reservoir caprock interface, and we have our well would be more or less equivalent to this one mountain up there. So we can look not just in the one dimension, but we have direct analog to look at reservoir architecture, caprock architecture, and so on. Some words on the reservoir. It's, as I said, sandstone dominated siliciclastic unit with a lot of fractures. The fractures sometimes are related to fault zones, not so often, but sometimes fault zones. There are locally also these igneous intrusions, both as dikes and as sills, which we also drilled through. We have tried to kind of develop a conceptual model where fluids migrate depending on how we see this fracture network. One of the, again, interesting learnings from doing the injection test, that within the CO2 lab well park, we have two boreholes, the H7 and the H5, which are very close to each other. And this is the upper part of the reservoir, so about 20 meters or so. And we have injected water to this borehole and measured pressure and temperature in the other borehole, and there was no communication, which implies that there has have to be some sort of barriers in here. We discussed whether these intrusions can be a cause or something else, but in the end we are arguing it's most likely these meter scale normal faults. And here's also an example of one of the outcrops locality where you see similar features exposed roughly 15 kilometers away, but similar geometries of these fault systems. So this is again the pressure. So heavily under pressured here in the reservoir interface, and slightly over pressured in the kind of shallow aquifer. And in the shallow aquifer, we also have some gas accumulation. It's a quite nice it's a few tens of meters of gas, which is appears to be kept directly by the permafrost. And we also have some artesian flow of water from this unit. So to us, this very much implies that the top seal is fine. One of the things, of course, is a smart drilling webinar. So as I said before, I'm not a driller myself. What we did with the drilling, we have subcontracted the kind of following up the drilling to some of the people from oil and gas industry, consultants there. And they've also summarized a lot of this in some reports. There's a freely available report on our website, so you can look at the main details. The key point from a geologist's point of view, we have these 8 boreholes, injection tests, and that we have this fault zone where we had always have to put the casing shoe below just to make sure we don't lose the wells. That's what happened with a couple of the earlier wells, that we didn't manage to get through this fault zone without introducing water in the system. Then the clay starts swelling and then things starting getting stuck. So we actually had to add one more diameter above it. Yes. So when it comes to the learnings from the test program, here are some of the values. Here are the red units are the ones where we have been doing the injection test to more or less calibrate our models and derive permeabilities. And it's important that, for example, if you look at the lower part here, lower 100 meter of the reservoir, this water injection test, and it was the first one we did in the open hole test in the DH4 borehole, where we saw from the core plugs that the porosity should be quite low and permeability also quite low. But from the well injection tests, we saw that it's actually an order of magnitude larger because the fracture network contributes a lot. In the upper part of the reservoir, it's a much better matrix porosity, so a little better matrix porosity, so the fracture network is not so significant, but still important. And then we've got this leak-off tests in 3 parts of the caprock, which tell us how far we can enhance the pressure to before we get fracturing. So to bring us, to bring us to the conclusion, we have shown that we have an efficient seal. We have a under pressured reservoir with confirmed storage capacity and injectivity. We rely on fractures to improve our fluid flow, our permeabilities, and we also have a sort of unconventional segmented reservoir. I haven't spent much time talking about the natural gas, but the natural gas is definitely thermogenic. It's at several different stratigraphic levels, and current understanding we have now from isotope analysis that this gas is actually a kind of shale gas play, which is of course very interesting to follow up also in the current discussion on what Svalbard should be powered by or get its energy from in the future. If they close, for example, the Goldfield power plant, maybe gas is an option. I also haven't mentioned the challenge. So I said we used about 10 million euro on the subsurface geological. So we are quite happy with respect to the storage part. I think there we are ready. On the top side, the investments to actually capture the CO2 from the coal-fueled power plant are prohibitive, maybe 10 times more. So we are looking at options of maybe securing CO2, not as import. I think this would work on Svalbard with environmental legislation, but perhaps like they do in Iceland with this Climeworks system from the air, or even just using the flue gas could also be an option. Because what we really need, we need to work on getting the CO2 down underground to get us further. Some of the visions we have up here more or less want to become a test site for onshore storage. Here, focusing primarily maybe on monitoring techniques, thinking about crosswell, and of course the reservoir is not the world's best reservoir, but sometimes at least it's local, it's very relevant and useful up here. And we have this unique system that we could be within 7 kilometers of everything on the whole value chain. We are also partner in many of the Norwegian CCS projects, both NCCS and also Success and various climate financed research projects where our experience is fed into the other industrial projects we have going on. And we are also, say, what the project is more or less on, say, not on hold, but we are kind of no basic financing. But the nice thing about finishing of phase 2 in 2015 is that essentially all the data and all the partners agree that data, if there are spin-off projects, or if there are interested parties to follow up, we are happy to share our results, which is also I'm here today. The last point, there are some of the, we are still a university. Our main goal is to educate the next generation of essentially Arctic science experts. And there is a master PhD course which is running at UNIS every year on essentially the CO2 project and how we can use geological constraints to improve this. With that, I'd like to thank you for your attention. This is the website of the project. This is my email if you want to get any more information. This is what the site looks like now in summertime. So the house we didn't build, it used to be there for Northern Lights research. Now we turned our look not looking up, but looking down. And I listed just a couple of papers which may be relevant, but there are lots and other papers which I can provide if you drop me an email. And of course, if somebody has any questions, let me know.
Thank you very much, Kim, for this interesting presentation from an unusual environment for many of us, I would say. And also, I would like to apologize for the technical difficulties with our connection to the webinar that we have hopefully well overcome in the end. We have already 4 questions in writing available. So the first one is by Jan Legalo. And the question is, what is the completion of the slim hole? And maybe I would myself attach one more question, similar sense. I would be curious if this using of the slim holes limited somehow your work, for instance, concerning the size of the cores for lab tests or installation of any monitoring or measurement equipment in the well. So if you can a bit more talk about the slim holes now.
Yeah, sure. Let's go back to, maybe this one is the best slide for this. So maybe go to the simple one first. So we have the, for us, we were at this exploration stage. The most important was to get the core out and looking at porosity, permeability, sedimentary phases, fracture mapping, these sort of things. And then it was quite fine. But I would have preferred to have a lot more wireline logs. And for example, down in the lowermost part, we cannot even get the gamma instrument down. And in this part, we couldn't get the sonic in. And with respect to the microseismic, that was the one which was the widest. The microseismic sensors we had deployed in the downhole. In this borehole, we actually couldn't get it down below the, this detachment zone. So of course there was some issue. There was some challenges with using this kind of equipment. But on the other hand, you also have to think that when we have a drill rig available here on Svalbard, we cannot choose to use something which is located on a different continent or even mainland Europe, given our location. With respect to the completion, what we have now, we are kind of plugged and abandoned them all. Let's go back to this one example. We can take it on. We can take it on this one maybe, because that's the deepest. And essentially all the ones, DH5, DH4, DH6, and DH7, they all go to more or less reservoir depth. DH6 is for the capital, and there we have more or less cemented everything and inside a borehole. So there, if we need to do any more work on subsurface, we need to actually go and drill new wells.
Okay, thank you. I'm not sure if this was a satisfactory answer to the completion question. Maybe Jan can react on the questions window again. And I will now take, in the meantime, a question by Tom Wildenborg, asking what are specific requirements for drilling onshore in Arctic conditions?
There's actually documents. People don't really know this, but there has been oil and gas exploration onshore Svalbard before Norway started exploring offshore. So early 60s, There was an American company called Caltex. They drilled a 3.3 kilometer deep borehole with a proper drill rig here. That remains the deepest borehole to be drilled. But there were 16 other exploration boreholes for oil and gas. There has also been hundreds of drilling for coal. And there are quite specific requirements as documents on what needs to be done from a kind of operational point of view. I'm happy to share these documents if anybody is interested. With respect to the practical issues, of course, some of the most clearest thing is to do with the seasons. And for example, having access to water, which is not frozen, really limits you either need to thaw your snow to get the water for the drilling, or you need to be doing this within a relatively short summer window when the water is actually flowing and not frozen. We have used both techniques during these drillings actually.
Thank you. And there is another question by Jan asking, how could you define the water injection zone, especially in the lower part?
So this was the lowermost 100 meters. And the way we are not defined, but we more or less did this with there was the part below the casing that stopped. So we had a 100-meter section of of the lowermost 100 meters of the reservoir, and we kind of sealed it off at the top and injected water in there to derive the permeability. So it's of course it's uncertainty. We did with that particular unit, the lower third, it has probably the lowest porosity and permeability and lowest net to gross. And there's of course uncertainty which interval does this water actually go to. But that's that was for the lower part there. 100 meter, and then the upper one with the two wells I talked about. This is just a 20-30 meter section, but this includes both the reservoir and part of the cap rock.
Okay, thank you for the answer. And there is one more question by Ton Wildenborg. Do you think that the Longyearbyen test site will develop to an actual storage site for the CO2 produced by the coal-fired power plant on Svalbard?
I would hope so, but I'm not so sure if this full-scale project is in agreement with what the politicians are currently doing. As I said, if you follow the Norwegian Oil Fund, for example, they cut all its funding to coal exploration over the whole world, and also they are closing the major coal mine here on Svalbard, not in Longyearbyen, but in Svea. So they are really trying to get away from anything involving coal. What I think may be interesting, and there is actually a process ongoing, so by summer the government should have a report on what are the options for actually powering Longyearbyen and the rest of Svalbard in the future. And there's many different options being discussed, including cable from the mainland, solar power, wind power, geothermal, coal, gas, whatnot, which is going to kind of at least highlight the not just the economic costs and the CO2 kind of emission costs, let's say, but also the socio-economic aspects of these different energy sources. So hopefully we'll know a bit more in summertime. I am going I'm not pushing this huge. I don't feel that if we want to spend 1 billion krona on something, it's maybe not to save 60,000 tons of CO2 per year, but I would be very happy if we can get access to some CO2. Can be just a few tons per year to do kind of campaigns of injecting CO2 down into maybe a fault zone, uppermost part, and actually doing, for instance, this kind of controlled release experiments or something like this. So I think there's still potential, but I'm not so hopeful that we'll have a complete 60,000 tons of CO2 per year anytime soon. This needs to have a much stronger political support than we have in Norway right now.
Okay, thanks. I don't know if it makes you happier, but generally speaking, I think it's a big issue for all running or planned CO2 storage pilots around Europe to get the CO2 for the storage. I think also our next speaker can confirm this. So as I cannot see any other questions, neither in the questions window nor any raised hands. So I would like to thank you once again, Kim, for your interesting presentation and for the answers. Thank you very much.
Thank you.
And I will now change the presenter's role to Carlos de Dios, our last but not least speaker. And I will now try to arrange like we agreed before. That means the slides will go from my screen and Carlos will move them. So hopefully it will work.
You can move the slides a bit.
So now it should be okay, I hope. So the floor is yours, Carlos.
Yeah, but I cannot move the slides.
In such case, just please say next slide and I will move it.
Okay, thank you very much, Vit. Good afternoon to everybody. As Vit explained it, I am Carlos de Dios and my position in Sweden is the CO2 Geological Storage Manager. And in INEOS, Sweden is the Work Package 1 leader. My presentation is focused on our expertise on well drilling at the Hontomin site. Hontomin is the Spanish project for CO2 geological storage and was designed and constructed in the framework of the project OXY B300. OXY B300, named Compostilla project, was the Spanish project funded by the European Energy Program for Recovery and the Spanish government. It's to enhance the CCS technologies. Please, next one. Next slide, please. Bit.
Yes, I'm trying, but maybe I got stuck a bit in my computer. Sorry about this. So I will try once again.
Okay, this is summarizing. The outline of this presentation is firstly some highlights on well drilling and the role that the drilling play for CO2 geological storage. Afterwards, some short explanation and description of Hontomin technology development plan and our experience on drilling, well logging, well completion, the monitoring, field tests conducted during the drilling phase. And finally, the main outcomes from this phase, from well drilling, and the future works we have planned in INEOS project. Next one, please.
Carlos, please try yourself once again. It should work now.
I can.
Good.
Oh, wait a moment. Okay. Okay, some highlights on drilling for CO2 geological storage. Regarding ONTOMIM project and afterwards the different research and development project where ONTOMIM was included and to then play the role of operator. We consider the CO2 geological storage as a waste removal technology. I mean, we don't consider any other added value as, for example, the EOR or EGR technologies. And this waste removal is focused in its permanent trapping into deep formations. In our case, ONTOMIM is a deep silane aquifer comprised mainly of limestone and dolomites, carbonates, and we will see in the next slide that with a very poor matrix porosity, so the fluid transmissivity is mainly through the fracture network. There isn't any doubt the drilling is a key role activity for site characterization and well equipment, and we consider drilling a key role activity that conditions the project feasibility. I mean, the drilling is probably with the some geophysical techniques for site characterization the most expensive activities during the site characterization and afterwards during the site construction. If we use the usual ONG industry standard rigs, the cost is quite expensive in comparison with using other technologies, as for example the mining techniques and the light drilling equipment. So, considering that the budget is reduced, using the ONG industry standard rigs, the number of wells drilled during the exploration and the amount of data available for reservoir characterization will be smaller than if we use a cheaper technology. We use the mining techniques with light drilling rigs during the well drilling and ONTOMIM. And this technology allowed us fully correct well test, in our case 2 wells, that cost less than those one drilled with traditional equipment. The main challenge we faced during this phase were, first of all, the maximum depth, because the usual depth to reach with this type of rigs, with these mining techniques, is 1,000 meters. To reach depths below this threshold is really difficult with this equipment. In our case, we reached the depth of 1,600 meters. Other challenge is the bottom hole diameter. In comparison with the bottom hole diameters drilled with oil and gas rigs, these diameters are smaller, and this parameter condition the dimension of the injection and observation tubings and the monitoring devices installed in the wells. And finally, the capability to integrate the usual well service like well drilling, logging while drilling, well completions with this type of rigs. I can move the slide now. Okay. Here you can see on the left side the lithological column with the different parts of the cap rock and the reservoir at ONTOMIM. As mentioned before, it's a deep silane aquifer comprised of carbonates, fractured carbonates with very low matrix porosity and fluid transmissivity through the fracture network. The main seal is the Marlias, located, the top is in the more or less 1,300 meters, and the bottom at 1,400 meters. And from this depth to 1,550 meters is the reservoir, the Sopeña formation. And finally, at the bottom is located the Kuiper. It's composed of anhydrides. 2 wells drilled on site with the depth, as mentioned, 1,600 meters, one for injection and the other for observation. Here you can see, afterwards in another slide, we will see the well completion, but in the injection well, the liner shoe reaches the top of the reservoir. And in the case of the observation well, the liner shoe reached the top of the seal, of the cap rock. Below this shoe, in both cases, the injection and the observation well, we drill it in open hole, and we are injecting the CO2 in open hole and measuring in the observation well in different intervals in open hole. It's allocated with 3 packers, flat cable packers, and in the injection well with a hydraulic packer. The distance between both wells at surface is 50 meters between the injection and the observation, and in depth is 180 meters, as you can see in the top image of the slide. So the pilot is compressed as well with a CO2 injection facility, water conditioning facility, and a control room. Sorry. What type of drilling rig we use at the Hunter Mill? You can see on the right side of the slide, the Segoki 2000 is a Spanish rig manufactured by the Spanish company, and is the usual rig for mining exploration, for groundwater exploration, with this usual threshold of 1,000 meters depth as maximum. On the left side of the slide, you can see the main technical features of this rig. It's with a mast height close to 60 meters, a maximum torque of 4,000 kilograms per kilopounds, better said, per meter. The Wheels load is 60 tons, and the combined cylinder and width total load is close to 100 tons. And the maximum pulse load is 20 tons, and the maximum speed is 120 revolutions per minute. I don't know if you are aware or it's useful for you this type of parameters, but I can say you that with this technical parameter, it's not easy to reach the depth of 1,600 meters. Other technical feature that is relevant is that the rig is mounted on a track, and for that reason it's mobile, and it's very easy, but that better said, quite easy, the placement and replacement on site. In this slide you can see the whole of the drilling equipment with the Segoki 2000, is the mining rig, and other components at the BOP. This is the mud fluid treatment. This is a screener. I'm sorry because the titles are in Spanish. These are the mud pools and other parts of the equipment like the pumps and auxiliary equipment. Regarding the performance of the works and the activities conducted on site for well drilling, in this case for the injection well drilling, on the right side you can see the depth time curve. In red color is the planned works, and the horizontal axis is the time, and in vertical is the depth, and in black color is the real evolution of the works during the drilling. The total period for each injection well drilling was 152 days. Regarding oil and gas performance, this is more or less between 2 and 3 times higher. But we will see in the next slides that the cost is as well between 2 and 3 times higher. The delay between the planet and the real works was close to 16 days, 1/6. That is acceptable for this type of works. If we see on the left side the activity allocation and the working period in percentage, we can see that the drilling, there isn't a doubt that the drilling is the most important activity in the well drilling for sure, and it's close to 50% of the working period. But other activities that must be considered to improve the efficiency and as well the safety of this drilling rig is the maneuvers, the piping placement and cementing, well logging. The matter is, what is better, the well logging or the measuring or logging while drilling? This is a matter to discuss in the work package 2 in INOS. On-site test, we will see what type of tests we conducted during the drilling phase. The final well completion is the typical completion, well heads, Christmas trees, but mainly the monitoring installation in depth. And finally, downtimes. As you can see here, we were lucky because to have downtimes close to 1.5 is adequate and reasonable value, with a total, as mentioned, of 152 days. The well logging we conducted on site during the drilling could be allocated in 2 different purposes. The first one is to acquire information from the different geological formation crossed during the drilling, and the second is for quality control purposes. For the first objective, it's possible. We can mention the gamma ray, temperature, neutron, spontaneous potential, resistivity, and sonic. These 6 well logging are the routine well logging, very useful for deep drilling, for oil and gas purposes, and for energy recovery, for geothermal recovery. Okay, the gamma ray, as you know, is to determine the amount of clay and the density, the temperature to determine the thermal gradient, neutron for determine the rock matrix porosity, spontaneous potential to consider and to define what is the limits of the aquifer and what is the potential brine movement. Resistivity is to determine the salinity and the conductivity of the brine, of the water, of the reservoir water and copper water. Sonic is to determine the velocity of waves P and S and how to correlate them with the mechanical properties, inertial extreme, elastic modulus, Poisson coefficient, mainly. And the acoustic televiewer. One of my questions to Eugene in his presentation that unfortunately Bit couldn't read was if one of the images in his presentation was the acoustic televiewer data. The acoustic televiewer is not, let's say, a routine well logging, and it's focused to identify the main fractures existing in the borehole. For the second goal, for quality control of well drilling, we can mention the caliper, gyroscope, and CBL. The caliper is used to determine the final inner diameter along the borehole. The gyroscope is used to determine some deviation and the well drilling path. And finally, the CBL is the cement bond log used to determine the cementing degree in different parts of the well completions, liners, and casings. Finally, the well completions for injection and observation well in Antomine, you can see in this slide. As mentioned before, we completed the wells with four different completions, 3 casings, 20, 13.38 and 9.58 inches, 3 casings, 1 liner, 7 inches that reaches, as mentioned, at the top of the reservoir. One injection tubing, 4 inches at the top and 2 7/8 inches at the lower part, anchored to the end of the liner, just over the shoe, with an hydraulic packer, and with a U-tube sampling system, a DTS, distributed temperature system, and distributed acoustic sensing system along the tubing. These 3 devices, the deep sampler and the temperature and acoustic devices for logging. 2 PT sensors installed below the hydraulic packer, just over here and here. And finally, 6 electrodes from the depth of 1,500 to 1,540, just over here. The observation well was completed in the same way that injection, with 3 casing, 20, 13.38 and 9.58 inches, 1 liner, 7 inches. In this case, the liner reaches the top of the reservoir, and with a tubing. In this case, the first case was made with super duplex material, and in this case is fiberglass material. It's 4.5 inches at the top and 2 7/8 to the bottom, anchored at the end of the liner with 1 inflatable packer, and as well allocating 3 different intervals with inflatable packers. This is the caprock, this is the upper part of the reservoir, composed of limestones, and the down part composed of dolomites. The tests conducted on field during the drilling phase were 3 different types. Here you can see 2 of the 3. Permeability test on field scale, connectivity test intervals, and leak-off test. First one is to determine the permeability in different intervals in the bottom hole at the reservoir. Okay, this is 1,400 meters is the bottom of the caprock, and 1,580 meters is the bottom of the reservoir. The results were interpreted with a code, a Zephyr code, it's analytic code, and was determined the permeability and the transmissivity for each interval. You can see here that the permeability is very low, considering that the permeability along the open hole is the much better area for the injection. I think this is not the forum and the webinar to explain how we improve the permeability on site. For sure, there will be another webinars and another meetings in Ines to discuss about it. After this permeability test, we conducted the connectivity test intervals. I mean, the interference test with 3 different dial schemes from the top to the bottom. This is the flow at the injection well. This is the bottom hole pressure at the observation well, and this is the bottom hole pressure evolution at the injection well. You can see here we start with different values of flow, and the evolution of the bottom hole pressure in this part is sinusoidal. Is clearly the behavior of a fractured reservoir with brine injection. So afterwards, we perform 3 different pulls, injecting and shutting, injecting and shutting, and detected the evolution in the observation well, and detected as well that the connectivity was possible and was a very important goal reached, because in this type of reservoir, very tight and with transmissivity through the fractures, is not easy to connect to the hydraulic connect both wells. So it meant that both wells were in the same geological block. And finally, main outcomes and future works. Regarding our expertise on well drilled Hontomin, we constructed 2 wells drilled to 1,600 meter depth with a cost efficiency of up to 60%, comparing the traditional drilling costs from oil and gas industry. And these wells were, or better said, in these wells, deep monitoring device for measuring bottom hole pressure, temperature, distributed acoustic along the well, distributed temperature along the well, electrodes and water samplings were installed and are working at this moment for Innos project. And regarding the future works, and regarding as well our role and our commitments in Innos project in the Work Package 2, mainly in TESC 2.3, named low-cost drilling, we want to develop a basic design of a drilling rig to reach the depth 2,500 meters using mining technique, using light drilling, and this is for sure a big challenge. And how we consider to do it, searching solution for technical gaps detected during the well drilling at Hontomin. Mainly the gaps related with the operation efficiency and safety. Other gaps related with well completion and installation of monitoring device. And finally, gaps related with the rig instrumentation and operation control. About these issues, I will talk on the workshop at Venice on April 23rd. And regarding the preliminary works we are performing at the deliverable 2.1 related with the task 2.3. And that is all from my side. If you have any question, I'll try to answer it. Thank you very much.
Thank you very much, Carlos. Are there any questions? I have to check again the questions table. And I cannot see any, unfortunately. So, are there any?
It's quite clear, everything. The meaning is no.
Everything was clear. I am now checking that if there are any raised hands among the attendees, but I cannot see any. Yes, there is a question. There is a question by Ton. For clarification, 60% cost efficiency means, and I will interpret it. Is it 60% cost saving or 40% cost saving?
60.
So it means
60% cost saving from the usual or for the usual oil and gas drilling techniques. As we handled during the tender, the drilling works tender at the 2012. 4 different offers with different budgets. 3 of them performed with the traditional drilling rig equipment, and 1 of them with the mining technique. And it was really very big difference between the budget, and was a risky decision to go ahead with the light drilling rigs. But finally, we can say that we reached the goal. If we didn't reach the depth with this completion and with the monitoring, probably I will not be here speaking about this issue, but we got it.
Okay, thank you for the clarification. In your presentation, there was a question on Eugene. So if Eugene is still online, could you please react to the question from Carlos that was related to the acoustic televiewer lock, if I remember well? So have you used it, and do you have experience with the result?
No, we haven't used the acoustic. No, we haven't. We don't have any experience at KGS doing
Okay.
this. I've seen it. I've heard about this, but we didn't touch it yet.
Okay,
Yes.
so thanks for the clarification. I think this answers your question, Carlos.
Yes, because it's. I mean, when I saw the image, it seemed quite similar to the televiewer image. I mean, because it's the televiewer image is representing the fractures with the azimuth and the dip. So, I mean, the fractures are oriented in the data from the acoustic televiewer, and as mentioned, it seemed to me that was similar to the acoustic televiewer, and for that reason, I made the question.
Sure.
Okay, so this was now clarified, I think. Are there any other questions? I cannot see any neither in the questions box. Are there any raised hands or oral questions? No? So if not, I think we can conclude our webinar. I think it was an interesting one, and I hope you enjoyed it. So thank you very much for your participation. Many thanks to all three presenters. And also many thanks to our colleagues from OGS for technical support of the webinar. Without this wouldn't be possible to organize it. And I hope you will stay with us for the next experience sharing focus group events. You are of course invited to visit our webpage. You are invited to take part in the workshop we will organize in Venice on Monday the 23rd of April. Or see you at the next webinar that will be organized later this year. So thank you very much once again. Take care and goodbye.